is a Royal Academy of Engineering Research Fellow and an academic at the University of Sheffield, but has been working in 3D imaging of energy materials of different flavours, from fuel cells to metal air batteries to lithium sulfur batteries, and now back looking at principally fuel cells and water electrolysers in the auspices of her Royal Academy of Engineering Fellowship at the University of Sheffield. So thank you, Jen, and we look forward to hearing what you say.
Super. So yeah, hopefully it will work. Thanks everyone for coming this evening, and thanks Paul for the invitation to talk. So yeah, as Paul mentioned, I'm an RAN research fellow working at the University of Sheffield, and my research is really concerned with trying to see inside energy materials, and so I'll explain all about that today.
I think if we just wiggle the cursor onto the right screen, then hopefully that will come to life.
There we go. So yeah, over the next 40 minutes, I'm going to try and zoom in and zoom out of the problem I think that we're really facing for electrochemical devices. So starting with a bit about what they are and why we need them, some challenges with the materials inside these devices, and specifically their failure mechanisms, which mean that we've not managed to scale up as rapidly as we would like to. How we can use multi-scale imaging to try and understand some of these failure mechanisms. And then I really want to end with a bit of a kind of zoomed out perspective on where I think imaging might be going, specifically for electrochemical devices, why it's important to consider sustainability when we're now thinking about the next generation of electrochemical technologies that we're developing, and then how we can start to think about engineering the kind of sustainable materials future. And so this is not my specialty at all, the kind of policy side of things, so I don't want to dwell on this for too long, but I think it's just worth acknowledging that we're in a kind of real transition point in our energy system, and really we have a huge challenge ahead of us to try and decarbonise a range of sectors. And I guess crucially for electrochemical technologies, really this energy sector represents around 76% of our greenhouse gas emissions. That's obviously huge. And then if you look kind of closer at what's contributing to this, these emissions, you can see that things like electricity and heat and transportation and manufacturing make up kind of most of these emissions. So these are really the areas that we're targeting with electrochemical technologies. And so they have a key role to play, but what are they? An electrochemical cell is, in essence, very simple. You have an electrolyte at the center, and you have two electrodes on either side. In these electrodes, we have redox reactions, and I think it's quite ironic. When I was doing my GCSE chemistry, we learned about oil rig, which is oxidation is loss and reduction is gain. So if anyone can come up with a new mnemonic that's clean and green, that would be great. And so in these electrochemical devices, we convert the chemical energy that's stored within the bonds of atoms and materials, and we convert that into electrical energy through the flow of electrons. And there's lots of news articles and news coverage on kind of range of electrochemical devices now that really highlights the kind of the scale of the challenge. Getting them into the right places is really hard. We have kind of like, where is it? Yeah, we've had kind of sort of more policy decisions, I guess, of the government saying, well, we need to really switch on our green hydrogen production now. We have some kind of safety concerns. There's a lot of concerns, I guess, with lithium-ion batteries in electric vehicles in terms of the rise of wildfires, for example, and not really understanding how to tackle those. Hydrogen refueling stations, I mean, this is the big topic at the moment, like will fuel cell electric vehicles or battery electric vehicles win out in terms of personal transport? And then there's also kind of cost concerns as well. So I think really it's quite a fascinating place to work. You really have to go through solving materials challenges at the atomic length through to kind of more global challenges. That's why it's a really interesting area. And on the bottom of that, I should say, getting enough in the right places is hard. I think there's a change in formatting in sending the slide through. Okay, so when we talk about electrochemical technologies, we have a kind of range of technologies available, and you can plot these on a Ragone plot. So you have energy density, i.e. how much energy this device or technology can store, versus the power density, which is kind of how easily and quickly it can deliver that energy. And this diagram, I suppose, really highlights why we need a range of technologies. We can't just rely on batteries alone or fuel cells alone. We really need to utilise all of the technologies that we have available, because something like a fuel cell can store a lot of energy in the hydrogen that it's using, but it can't deliver it as quickly as something like a supercapacitor, for example, which can't store a huge amount of energy, but it can deliver it very quickly. And I really liked this, this graphic shown on the right-hand side, that I think shows that really to target these different sectors, we'll need to use a kind of multi-pronged approach or a multi-electrochemical device approach. So something like personal transport, quite possibly electric vehicles have kind of won that race. I think we're seeing that in the uptake, albeit a kind of slowing off uptake of electric vehicles. But there's still big questions around like industrialization, or if you have a wind turbine that's blowing at 2 a.m, what do you do with the energy and the electricity that creates, and possibly converting that electricity into green hydrogen and then distributing that green hydrogen to somewhere that it's needed is a sensible thing to do to make sure we're kind of using all the energy that we have available. And then thinking about our electrochemical technologies, really we can tune the materials inside these technologies to our target application. And so although we have something that from a materials perspective should be really simple, we have 3 components and that's it. We have an electrolyte and these 2 electrodes and ions and electrons that flow. By changing the materials inside these technologies, you can change almost every property about them. So from a lithium-ion battery, which is like an intercalation chemistry where lithium is kind of intercalating and deintercalating from some transition metal oxide materials, through to the kind of metal air batteries, zinc air batteries, which have a kind of solid metal negative electrode, a zinc electrode, and we get kind of chemical reactions that happen. So there's a change of state of material in these types of batteries. Through to fuel cells and electrolysers, where a fuel cell delivers hydrogen and oxygen to the cell and we produce water and electricity. And then the exact reverse process, we use an electrolyser where we take water and put in green electricity, split that water molecule apart and create hydrogen and oxygen. And so it's a really interesting materials challenge then, because I think there's a lot that we can learn from each other working across these technologies, because quite often, I think we put ourselves into these research camps as researchers. So during my PhD, I was a fuel cell researcher nominally. But actually, although we're kind of sitting on these 2 technology groups, all of the challenges that we're facing and that we're trying to solve at the materials level are the same. We're all trying to study the diffusion of ions and electrons through these porous materials. We've all got lots of thermodynamics and kinetics challenges that need to be solved with catalysts or tuning the voltage of the 2 electrodes. And possibly the things that I'm most interested in is these bottom ones, so thinking about the degradation and the multi-time and length scale processes that happen in these technologies. And so that's kind of what I'm going to focus in on today. And so then specifically thinking about imaging, there's lots of challenges with imaging. It's not easy to do, but I think there's 2 key challenges that this kind of multi-scale approach can really solve. So the first kind of challenge is that all of these electrochemical technologies are multi-scale in nature. Their processes span length and time scales. So this is the fuel cell example. You go through from the kind of nanoscale, you're looking just at the atoms and the particles inside the catalyst layer, for example. So these are platinum nanoparticles decorated onto carbon nanoparticles. If you zoom out a little bit, you get through to the micro scale. So you get to these kind of electrodes and layers. So now we can understand something about how these catalyst particles are kind of manufactured and put together into these layered structures. But we don't quite have enough resolution to zoom into the kind of nanoporosity that's inside these catalyst layers here. And then if we zoom out even further, we get to the device level. So now we're looking at, in the fuel cell example, maybe where water is being formed inside our fuel cell. And at the same time as that, we have these multi-timescale processes. So catalysis happens in fractions of seconds, but something like degradation or even just operation of a battery vehicle, that lasts days to years to decades. And so trying to solve this kind of overall picture of how these things relate to each other, I think is one of the big challenges for imaging of electrochemical devices. But luckily, we have lots of tools at our disposal to kind of study these. So again, this is another fuel cell example where we used X-ray micro CT, so this kind of microscale technique to look at what's called a membrane electrode assembly, an MEA in a fuel cell. So what you can see here is the fibers in your gas diffusion layer. So you can kind of start to understand how gas is going to get through to this catalyst layer that's shown in yellow. But you can't resolve any kind of features about what's inside the catalyst layer. We have to treat it as a bulk structure. So then you can zoom in a little bit and you can use X-ray nano CT. So now we can start to say, well, how is the fiber interacting or embedding itself in the microporous layer, which is shown in kind of grey, and in the catalyst layer. And we maybe start to get some understanding of the morphology, but we really still have to treat these layers as kind of a bulk layer. But then we can use something like SEM to zoom in a little bit further and start to look at the kind of pore structure inside the catalyst layer, and understand a bit more about the pore sizes and the particle sizes in our SEM. And if we zoom in even further, then we can get to our TEM case. So now we can really look at these kind of 3 to 5 nanometer platinum nanoparticles. But I guess this also highlights that with TEM, you're looking at this, like, I don't know, 100 nanometer fraction of your catalyst layer. So then you have no knowledge of the kind of micro scale bulk performance or morphology, and vice versa. With the microscale, you can't look in at TEM. And so I just wanted to kind of zoom back out a bit, I guess, and give a quick overview of what tomography is, just to help kind of frame the rest of the talk. So when we do CT scan, we put our sample in between a source of either X-rays or neutrons and a detector. We collect what's called the radiographs, shown on the top right. And then we rotate that through 360 degrees, collecting projections. The kind of the grayscale value, I suppose, of the radiograph is based on this Beer-Lambert law. So heavy elements in X-rays attenuate the X-rays very strongly, so they appear dark in our radiographs. And then when we reconstruct them, they appear very bright in our kind of reconstructed volume. And then we're kind of free to study whatever processes we want to in that kind of 3D volume. And we also have some choices of whether we want to do kind of ex situ, in situ, or operando imaging. So if we're going to do ex situ, we just put a kind of punch out of our sample into our source, rotate it, do our CT scan, and we get a data set out. But really what we'd like to be able to do is attach a potentiostat to our operating cell and then take an imaging data set at time 0, cycle the cell a bit to degrade it or operate it, take another imaging data set, the same region, and another imaging data set, the same region, and so on. And so now we can go from a case where we have to take something out of the sample and destroy it to be able to study it, to something where we can operate it. We can visualize it as it's operating and see what's changing. And I really loved this paper that came out in 2022 that I think really highlights the kind of challenges or the benefits of doing these different approaches. So, you know, in ex situ, you've got to kill your fish to be able to study it. If you want to do in situ, you can put that fish in a fish bowl. So the fish is kind of seeing the environment it would expect to see, but from the outside, we kind of know we've made a few concessions with that approach. And then operando is where we're truly kind of operating the cell in its environment that it's fully used to. And I've talked a little bit about why we want to use X-rays and neutrons, and really these are complementary techniques. So the interaction of X-rays and neutrons with atoms is a bit different. The physics of it is a bit different. So whereas X-rays will interact with the electrons in the outer shells, neutrons will interact with the nucleus of an atom. And the result of this is that for X-rays across the periodic table, we basically scale linearly-ish in terms of the attenuation of X-rays. Neutrons have a slightly different, slightly strange interaction that I still don't really understand. But all I do know is that hydrogen has a very strong neutron cross-section. This means neutrons are attenuated really strongly for hydrogen. And so using the fuel cell as an example, we can really start to see the benefits of neutron imaging for trying to study some of these elements that are very light, like hydrogen. Lithium is another example. In terms of batteries, it has quite a strong neutron section as well. So you can see on the left And this is like a little in situ cell that I designed for some imaging. If you fill it with water and put it in an X-ray instrument, there's lots of kind of beam hardening effects. You can barely see the water at all. Amazing. So there is some water that you can sort of make out, but if you wanted to actually process this data and get some quantitative information about the water inside there, you would really struggle based on the quality of the image. If you put the exact same cell filled with water into a neutron source and do tomography, now you can basically not see the aluminium, the gold-coated aluminium cell at all, and we can really clearly resolve the water inside of this. But as with everything in this space, we have to make some concessions. So neutrons are really brilliant for studying water, studying hydrogen, and studying lithium, but they have a lot of challenges in terms of the kind of resolution that we can achieve with neutron techniques. So really, we can only get down to the kind of millimeter scale feature or the large micron features with neutrons, whereas with X-rays, we can really go down to the kind of micron and nanoscale. The other challenge, I think, for neutrons is that the flux of neutron sources is a lot lower than the flux of X-ray sources, so we can't go as fast if we're thinking about in situ or operando studies with neutrons, although it is improving all the time as reactors improve or spallation sources improve. But with X-rays, we can go really fast, so you can get a single tomogram or multiple single tomograms in less than 1 second now, which is pretty incredible. But again, not so good for light elements, whereas neutrons are really good. And so we can either, for X-rays, we can either use a lab-based source. So here in Oxford, there's multiple Versa instruments that you can use. And so for most things with X-rays, a lab-based source is probably acceptable. If you want to go really fast, you'd have to go to a synchrotron. And obviously, we can't have a nuclear reactor in anyone's research lab. So if you want to do any neutron imaging, then you have to go to a kind of reactor or spallation source as well. And the other benefit is you get a very nice breakfast looking out over the mountains. And it made me chuckle that the diamond light source was renamed Oxford University Particle Accelerator, but I don't think that name is going to stick. Okay, so just summing up this this kind of section, I guess then. So really, what we actually can do is combine the benefits of both of these approaches, both of these sources of imaging to do kind of multi-mode correlative imaging. So if you want to look down at this nano and micro scale, you might start to think about using X-rays. If we're looking at kind of macro scale and the water evolution or lithium distribution in lithium-ion batteries, then we can use neutrons. So that's one of the challenges with imaging. The other challenge with imaging in electrochemical devices is that they all have these failure modes, and all of these failure modes happen across multiple different length and time scales as well. And all of them occur at hidden interfaces. So again, I think this is the kind of beauty of 3D imaging, is that we can now really access these 3D interfaces between the layers. So some of the challenges in different battery chemistries, we might get passivation. So in the case of a zinc air battery, you go from zinc to zinc oxide, and going back is very challenging. You might get unwanted side reactions leading to gas formation. Again, in the kind of metal air space, you might get dendrite formation. So when you're reversibly plating, the lithium or zinc will just plate back onto a cluster of zinc that already exists. And so you'll get dendrites, which will lead to short circuits. And really, most of these things ultimately lead to some sort of catastrophic cell failure. So they're really a safety concern as well as just a practical operation concern. And in fuel cells and electrolysers, we have a kind of similar set of degradation mechanisms. So, and again, these are across length scales. So really at the nanoscale, you might get some catalyst corrosion or agglomeration. At the micron scale, catalyst layer, it might start cracking or delaminating. And we also get kind of water management, either water being fed in through the electrolyser or water kind of trying to be removed through the fuel cell. So to kind of, I suppose, show how we can use X-rays and neutrons in a complementary way to understand some of these degradation modes, I'm just going to zoom in on the fuel cell. But before we even operate our fuel cell, I think one of the key challenges we're facing with the manufacturing of electrochemical devices is that no matter how perfectly you try and create your your electrode layer, your MEA, you're always going to have some inhomogeneity that's present from the start. So this was a very simple study, but I think it made a really interesting point. So we basically took a small punch, so 2 millimeter diameter punch out of a 25 centimeter squared membrane electrode assembly in a fuel cell. Before it had been operated, we just kind of manufactured it and then took the punches out. And if you look at the volume fraction that's calculated for each of these layers, the catalyst layer, the microporous layer, the gas diffusion layer, you can see already there's like quite a lot of inhomogeneity and differences in the volume fraction of these three components across all these 9 regions. But what's kind of more telling, I suppose, if you zoom in on one property, so in this case looking at the tortuosity factor, which is essentially like how easy can species diffuse from the top of the electrode or the gas diffusion layer in this case through to the bottom, and you do the tau factor on each of these 9 regions, you see huge differences in the tortuosity factor value and the porosity factor value across the GDL for these 9 regions. And I did some work with Pablo, who at the time was at UC3M in Madrid, and he did some image-based modeling. So I gave him the CT scans, and he put the values from those images into his model to basically predict what the limiting current density or the expected current density across these 9 regions would be. And what we found was that there was huge differences in the expected current density across these 9 regions, up to like half an amp per centimeter squared, which for a fuel cell is really significant. And actually, you can also do other techniques, like this is a current mapping technique that I was involved in. And I think just focusing on this example is kind of the most interesting, I suppose. So at very low voltages, which is very high current densities, where you're producing a lot of water, you're having a lot of fuel cell reactions. You can start to see that if you map the current across this, then it kind of tallies with what we were seeing from the modeling work and the image-based modeling work, that really from the start there's lots of inhomogeneities across the cell. And this also impacts the way that water is produced. So in this study, we designed a kind of small cell that you can see up here that was suitable for neutron imaging. And this we called high speed. We did a single tomogram in 36 seconds, which is very high speed for neutrons. But if you do X-rays, you might think that's really slow. But what was really great about this is that for the first time, we could then track the volume of water that was being evolved in the kind of 3 different components in the fuel cell. So in the cathode flow field shown in blue up there, in the MEA, the membrane electrode assembly, and in the anode flow field shown in red. And we're quite interested in this kind of higher current density region here. So this is a fuel cell polarization curve. And the higher the current density, the more water you're evolving because you're doing more reactions, but the performance is starting to decrease. And so let's just take 400 milliamps per centimeter squared as an example. So somewhere in the middle, we can now start to kind of qualitatively understand where water was going inside these flow channels. In this particular cell, there was quite a bad problem with back diffusion. So really, there shouldn't be any water on the anode, but because of the kind of room temperature operation, we were kind of dragging water back across to the anode. But because we're now doing tomography rather than just kind of 2D radiography, we can also quantify the volume of water that's formed in the cell, and then conversely kind of calculate like a removal rate of the water. So comparing using the Faraday law, you can basically calculate theoretically how much water should be evolved in the fuel cell over time. And so we can see that in all cases, as you increase the current density, the volume of water is increasing. But we are still removing some water. So that's a good thing for a fuel cell because you don't want it to flood. And then we went on to say, well, that's the case for these kind of single serpentine flow channels that you can see here, which are pretty standard in fuel cells. But what happens if you change that flow field design? What happens to the water distribution? And so we kind of evolved the experimental setup at the same time. So now we could continuously rotate the cell and half the amount of time it took to collect a single scan. So now we were doing a single tomogram in 18 seconds. And from our polarization curves, you can't see a huge difference in the cell performance. You can definitely see the parallel cell is not performing as well as these single and double serpentine designs. But it's really only when we started to look at the imaging that you could really see clearly why this parallel cell was failing so dramatically, or so bad at doing this water management. So on the top, you can see the 400 milliamp per centimeter squared hold. And as on the previous slide, you can see that the volume of water inside the cathode for the parallel cell is much larger than the single and double serpentine. And then when you start looking kind of at the corresponding tomography data sets, you can really see, particularly in this case of this parallel cell, that 3 out of our 4 flow channels are just becoming completely filled with water. And the light blue is the cathode and the dark blue is the anode. So we're also getting a lot of back diffusion of water in the parallel cell. Whereas in the single and double serpentine cells, we're not doing too badly with water formation. In the single cell, a lot of it is focusing around here. And then at some point, there's like a big slug that's maybe removed or pushed out of the cell. And interestingly, I thought the double serpentine was like this intermediate case where you have 2 channels available, but one of them essentially after a while is completely cleared of water and the other one becomes kind of pretty full up. And you can start to do some kind of basic, very basic modeling to understand why this might be. So there's an equation called the continuity equation that basically says that the area times the velocity of flow in must equal the area times velocity of flow out. And so particularly in the case of this parallel cell, because we're quadrupling the area that the gas has to flow through, we're going to quarter the velocity of that gas flow. And so the result of that is that there's just less or slower gas flow pushing the water out of the cell. And so it's much more prone to flooding than in the single and double serpentine cases. And I suppose what's most interesting in these kind of multi-channel designs is that in both of them, they kind of pushed all the water out in one flow channel, leaving it free. And I think what's particularly interesting for that is that if you think about degradation, for example, if you've only got one of your flow channels that's electrochemically active, then over the long term, that's going to lead to significant degradation. And because we were doing 4D imaging, we could also look at kind of droplets inside our channels as well. So we could now understand a little bit more about the kind of types of droplets that were evolved and the behavior of the droplets inside the cell. And Dan Niblett at Newcastle, who was at Manchester at the time, had done some modelling work to kind of predict the types of droplets that would be evolved in flow channels. And what we found is that we could basically identify all of these types of droplets that he had kind of predicted from his modelling studies. So it was a really nice experimental demonstration of that. And I just touched on this, but the other kind of problem is that if we've got all these inhomogeneities right at the start, then when we degrade our cell over thousands of cycles, so this is just some plots showing the types of long duration cycling we can do in fuel cells to degrade them on a timescale that's kind of reasonable to do in the research lab, so days to weeks, not 10 years. You really start to see that this leads to quite a marked effect in the degradation rate across our fuel cell at the end. So here's our polarization curves of this cell that we degraded. So from 0 cycles through to 5,000 cycles, the performance has completely died in this cell. And so what was quite interesting then is saying, well, rather than just focusing on one region of our fuel cell, what happens if we take multiple regions of our fuel cells and compare them? What happens to the morphology of these regions? And sure enough, we saw huge differences in the kind of rate of degradation of these 3 different regions. So shown on the left is the thickness map of the catalyst layer, and shown on the right is the cracking map. So that's kind of like the absence of material mapped and segmented. So there's a few different features you can see. The kind of dashed lines are the outline of the flow channel at that region. So the first thing that you kind of note, which was kind of shown in previous studies as well, is that under these channel regions, so anywhere that the channel is kind of flowing through, these are the channel regions, the extent of this cracking and failure is greater. And this makes sense because there's more gas flow through these regions, so there's more electrochemical reactions happening, so there's more degradation over the course of the degradation mechanism. But I think what was most interesting for this study is that actually the rate of the degradation across the 3 regions was significantly different. So the outlet where kind of at the end of the gas flow is much more degraded than the inlet. And again, that kind of makes sense because you've got a lot of gas right at the start when you're putting your gas into the inlet. And by the time you've reached the outlet, you've kind of used up a lot of that gas supply. And so the amount of gas available at the outlet is much smaller. And so I suppose through starvation of gas, you'll get a faster degradation rate. And again, we can start to do some of these multi-scale approaches. So on the left, you can see just an example of one of these crack networks that I would kind of love to go back and study in even more detail to try and understand exactly what's happening at the kind of T-junction of one of these cracks to say, why is it, cracking in that particular region? But overall, you can kind of see that some cracks that were present in the starting material got a lot wider, they extended a lot further, and then at some point, new crack networks formed within these materials. And at the end of life, we took like a scrape of material from each of these samples and did some TEM to look at the particles. And yeah, what we could see is that along with kind of this cracking mechanism and failure, we're also getting agglomeration of some of the platinum nanoparticles as well. And so overall, what's really happening throughout this degradation process is you're going from this fresh catalyst layer case. We've got a nice, well-connected pore network, so water can get out very easily. We've got very good electrical contact between all of our carbon nanoparticles. And we've got this quite open pore network. And when we degrade our cell, this whole pore network is collapsing. It's harder for water to get out. The platinum nanoparticles are agglomerating. And so it's no surprise then that the performance of this cell is drastically reduced. So that's kind of a macro to nanoscale view of a fuel cell. But I also wanted to touch on some other kind of completely tangential studies that we've kind of done a lot of these with Paul as well over the last few years too, where we're really harnessing the power of X-rays and or neutrons to kind of study some effects, some degradation effects in electrochemical devices. So yeah, we're switching tack entirely to lithium-ion batteries, but this was a synchrotron study, so now we're kind of using X-rays to go really, really fast. This particular study was interested with understanding what happens when a cell would short circuit or there was a defect in the starting material, what would happen to the failure mechanism of that material based on where that defect was. And so this was in collaboration with NASA and NREL, and the team designed these kind of internal short circuit devices that you can trigger, and that kind of reflects what, like a material's failure, and that would lead to some failure mode. So we use these specially designed calorimeters to understand the thermal properties of this catastrophic failure in conjunction with imaging. So you're kind of imaging through this region of these calorimeters to then study the cell as it's failing. And also these studies were really cool. So yeah, it was a really interesting case study of using high-speed CT. So just one example from the work shown here, where we're placing the ISC at the top of this 18650 cell, and we're trying to understand what sort of failure mechanisms are happening. So the first thing we did was thermal imaging, so taking 50 frames per second. Hopefully, yeah, the video will load. And after a short amount of time of heating the cell, you can see there's this absolutely catastrophic explosion and failure of the battery. And you can start to see, ejection of the jelly roll material right at the end of the kind of failure. If you do the high-speed imaging, which hopefully should play, you can start to see why this is happening or where the kind of source of this failure is happening. And at some point, around about now, you can see this gas escaping from this breach in the top can of the cell. And that's shown better in this picture down here. And so, in the case of the ISC in the top of the cell, you're seeing a lot more kind of top failure of or top venting of these 18650 cells. If the failure mode or the ISC was near the bottom, then you'd get a lot more bottom venting. And we could also see that, the temperature difference, the temperature gradient across the cell was around 200 degrees C from the kind of point of failure where the ISC was to the other side of the cell. So there's lots of thermal challenges to be overcome as well. So I think this was just a really nice study where, using high-speed CT, we could really start to understand how we might test batteries in the future, kind of new chemistries to understand how they might fail, but also to really understand the source of the failure. So we can use X-rays to go really fast. We can also use X-rays to go really slow. So I talked about zinc air batteries a little bit at the start. Zinc air batteries, in theory, are really promising battery material or battery technology. Zinc is very abundant and very cheap. And so if we could get them to work, then they'd be a kind of great alternative to some of the lithium-based chemistries. But I spent 2 years of a fellowship trying to make these reversible and without much success. And from studying some primary zinc air batteries, you could really understand why. So this cell is massively magnified. They're only like 7 millimeters in diameter in real life. And the only real application of zinc air batteries at the moment is in hearing aid cells. So for hearing aid cells, they're great because they deliver energy really slowly. You can see this discharge is a C/90 discharge. So that's discharging the battery in 90 hours. Compare that to kind of under 1 hour for a lithium-ion battery. So they're really quite slow. And what you see if we do kind of in situ CT along this discharge is that we start from this nice zinc particle phase state. We have oxygen that's coming in from the bottom here through some holes and through the kind of separator that's shown by this kind of nickel weave. And so as we go through the discharge, we're kind of discharging the material, or we're converting zinc to zinc oxide from the bottom of our cell through to the top of our cell. And the difference, obviously, in the morphology of the zinc particles to this kind of discharged zinc oxide state is very significant. And I was also quite interested to understand, well, what's the effective rate of discharge on the morphology of the cells? And actually, what's interesting is that even at, what's in reality a very slow discharge, so a C/30 discharge, you reach the cutoff voltage of 1.1 that's kind of recommended by the manufacturer after only around 5 hours. And what this means in practice is, if you look at the top, you essentially have all this underutilized zinc. And even if you go to kind of a C/150 discharge, you can still only get to around 85% of the mass utilization. And it's not that hard to understand, I suppose, why this is happening. So zinc oxide is not very conductive at all. And because of the design of these batteries in 3D, you're really having to get electrons that are going from this outer shell through all of this zinc oxide material and zinc material for any of these electrochemical reactions to happen. And so then thinking about trying to make these reversible again is even more challenging, because how do you go from something that's like a big blob of bulk zinc oxide back to the kind of zinc particle state? And so there's a few ideas of how this could possibly be done. And again, I had a few ideas too. You could maybe grow some zinc onto like a sponge material and then grow and shrink the sponge into this pore. Yeah, amongst other kind of techniques. But yeah, I think it was just a kind of nice demonstration of some of the challenges we have to make batteries like this rechargeable. Okay, so for the last kind of 10 minutes, I'm just going to zoom out a little bit and talk about where we might be going. So obviously AI is like the word on everyone's lips at the moment. And I think for imaging, it's going to be increasingly important. One thing that's great about sources getting better is that we can go faster, we can scan more samples, we can have higher resolutions, and as a result of this, we can generate even more data. But I suppose the question is then, what can we do with that data? So this is one paper that was published quite recently in Nature Communications, where it was possible to do what's called super resolution. So now you can basically scan one region of a fuel cell, in this case, in very low resolution. You can scan the same location in very high resolution, and then you can use AI to superimpose the high resolution of that high-res scan onto the low resolution of the large field of view scan. So you get one data set out at the end that has the resolution of a very kind of high-res scan. I guess the challenge here is that it takes kind of 11 hours to get the high-res scan. So for in-situ studies, still a long way to go. But the benefit of that is that you can kind of combine this multimodal kind of correlative multi-scale imaging, I suppose. And so now you can then start to say, well, we have the resolution of a large area. And so we can model that large area and say, where is the water going to be formed in the fuel cell, for example. So that's one example of some work from the literature that I think is really promising. The other example is using it's kind of multimodal imaging. So taking the same or a similar cell, so in this case, an 18650 cell, using some high-speed tomography in kind of 2.8 seconds to get some microstructural information about like delamination, for example, in the electrodes, and then doing some neutron tomography to look at the kind of lithium distribution inside our cell. And I think the great thing or the promising thing about this multimodal kind of approach is that going to a synchrotron source, these facilities are generally right next door. So in theory, it would be possible to kind of go and do one experiment on one day and then take the same sample next door and go and do the same experiment using the different source the next day. And I suppose the final kind of perspective I have on the future of imaging is really, understanding how to start using some of this data better. So in one single B time, you might go and collect a full hard drive, 5 terabyte hard drive worth of data. So as one person sitting through and trying to analyze all that data is really, really hard. And so I think we're kind of moving towards a place where we can start to use some of these AI tools to do some of that segmentation work for us and start to kind of understand the whole data set rather than just the one portion of this data set that we can understand as one human. And I think the other thing is that we can start reproducing things and understanding the uncertainties in our experiments a bit more. So, this paper by Graham Smith and Ed Dickinson at MPL kind of highlights this, that it's really hard to do for electrochemical technologies, because if you build 2 batteries or 2 fuel cells with exactly the same starting materials, they'll probably perform differently. It's almost impossible to get a cell that performs the same. And so I think we need to start understanding what is acceptable when we say, well, cell A has one performance and cell B has a different performance, but actually their degradation properties are the same. And so we can be confident that that is the degradation mode that we're seeing. And then just to finish off the kind of final few slides, I think zooming back out to this kind of larger problem that we're facing. So again, it's been in the news recently that although AI is absolutely brilliant, I think it relies heavily on energy production and water for cooling. And so what are some of the ways that we can start to think about designing electrochemical materials that is kind of more sustainable? And I think this is well visualized with the periodic table. So we have all of these 118-ish elements available at our disposal to use in our electrochemical technologies. But if you start mapping lithium ion and emerging battery technologies and flow battery technologies and fuel cells and electrolysers, then you quickly use up most of the periodic table. And these elements are only available in finite supply. And there's a criticality assessment from the UK Critical Minerals Intelligence Centre that says what are the critical minerals at the moment. And generally, most of the materials or the minerals that we're using in our electrochemical technologies are also critical. So what we need now is some strategies to make sure that we're using these finite supply of elements in the most sensible way. And there's also some environmental challenges. So PFAS is something that we're also talking about a lot more now. These are the kind of forever chemicals, the fluorinated carbon backbones that are found in Teflon in frying pans as a good example, but they're also in the naphthalene in fuel cells and electrolysers. They're found in the kind of binders and electrolytes in lithium ion batteries. And where we're really struggling here is that any analog, so like CMC binder alternative for a lithium ion battery, they just don't perform as well, and they don't meet the kind of KPIs that have been set in terms of performance versus the kind of PFAS based materials at the moment. And there's not enough clarity on legislation and regulation. So are we even in the future going to be allowed to make fuel cells and electrolyzers from naphthalene? And if not, then what's the solution? So I think there's lots of challenges there, kind of already arriving or coming down the line in terms of the way that we make electrochemical devices. And so something I've been thinking a lot about recently is well, what are the strategies then to address these challenges? And I think from looking at the literature of all electrochemical technologies, there's kind of 4 key ways that I think we can start to be going in terms of the next generation of materials for electrochemical technologies. I think this paper will be very familiar to a lot of people, but if we can make them last longer, then obviously we can make the materials that we're putting into these devices go even further. We can use alternative materials. So in an electrolyzer, for example, iridium is the main catalyst that's used, but only 7,000 kilos of iridium are mined every year. So it's a tiny number. So we really have hardly any iridium to use. But what about if we start to use something like ruthenium, which has kind of relatively similar catalyst properties to iridium, but is much more abundant? And thinking about batteries, for example, the talk that was a few weeks ago on LFP and LMFP battery cathodes, maybe we can start to rely on those instead of these lithium iron phosphate, so iron rather than nickel and cobalt, for example. We can really try to drive down the amount of them that we're using. So this is the technical targets from the US Department of Energy, and it says that ultimately we need to get to 0.125 milligrams per centimeter squared of platinum group loading inside electrolyzers in this case. And at the moment we're at 3 milligrams per centimeter squared. That's quite a significant reduction in the volume of platinum and iridium that we're using. But if we can use less of it, then the materials we do have will go further. And then finally, we can start to think about recycling. So I'm having increasingly more discussions about what we do with these materials at the end of life. And I think there's already some great work going on in the battery space in terms of one of the Faraday Institution programs looking at reuse and recycling of batteries. And there's also kind of an uptick in the literature of, well, what are some alternative strategies or materials to kind of recycle the iridium content in an electrolyzer, for example. Okay, so the formatting has failed slightly on this, but so I'll just actually put all of the funky animations on. So yeah, just to kind of summarize the talk, thinking about energy and decarbonisation of our energy system is very challenging, but electrochemical technologies can go a long way to help with decarbonising some of these key sectors, so transport and industry. Multi-scale imaging is a great tool for understanding how the materials in these devices operate and fail. And then I kind of touched on, I guess like the next generation of imaging, how we can use AI and multimodal imaging to start to understand even more about our battery material and electrochemical materials, and then how we can start to kind of approach some of these bigger sustainability questions and criticality questions in electrochemical devices too. So just to finish off by thanking my research group, which I don't have a picture for yet. We're very small, so I'm waiting for some sun to come out in Sheffield so we can go and take that picture. And then, a huge thank you to all the collaborators from over the years, I suppose from the EIL particularly, and then from the neutron sources as well. And then I just wanted to leave this slide here. So currently with Josh Bailey, who's at Queen, who works in Belfast, and we're editing a special issue on this question of standardization. So if anyone has any papers that they think might be relevant for this special collection, then please do get in touch about that. But otherwise, thank you for your attention. Happy to take any questions.
Right, thank you very much, Jen. Really interesting. While you get some water, any questions from the room?
Really, really cool. And obviously all the tomography is incredible. And you talk about it becoming kind of higher performance, higher resolution, more data, harder to process, harder to store. Is there much being done to make these techniques more accessible as well as higher performing, as opposed to potentially less accessible as the data sets grow?
More accessible in what sense?
In terms of resources for researchers, say, if you don't have access to high performance computing, how do you analyze 10 terabytes of data?
Yeah, I suppose at beamlines now, a lot of the beamlines are kind of integrating data processing into their workflow. So like the neutron tomography work, Ralph, who I was collaborating with, had to go and reconstruct all those data sets himself, but I wouldn't have been able to do that myself for sure. So I think, yeah, a lot of work is happening now so that when you leave the beam, you can have your kind of packaged process data and then go and study in your research lab. I suppose in terms of access to HPC, I suppose the Voice has some HPCs that you can access kind of nationally. So there are kind of schemes that you can access to yeah, process large volumes. But it's a very good question. Yeah.
Two things that I would maybe add to that as well is so Diamond and a lot of synchrotrons now give you a data beam time. You have to apply for it at the same time, but it means you can go and use all their HPC facilities or their software licenses subsequent to doing your beam time, which is that nice add-on. They're also really good at curating the data and storing it on a long-term, glacial storage for you as well. And then the CCPI, the Combined Computational Project Imaging, has quite a broad portfolio of available software, some of which runs in the cloud, but a lot of it you sort of download yourself. But it's quite efficient, and it allows, if you're familiar with sort of ImageJ, it's got sort of ImageJ type plugins, but are much more sophisticated. So it's still got a really accessible GUI, still runs pretty efficiently even on a well-spec laptop, but it's got some really sophisticated processing. It's all free. Sorry, so just a couple of additional things. I think it's a really good question. So. Yeah. Yes, next question.
Thank you very much. Congratulations, it's a very good talk. And my question is about multi-scale calculation of the energy storage devices, because when we talk about multi-scale, we are talking about different technology as well. There may or may not be overlap. And for each technology, there are advantages and disadvantages. Do you have some comment on how we can link the technology or observation together so that we can find something new? Because I think at the moment it's kind of like everyone focus on something specific, not necessary to bridge the gap or have collective thinking on that area.
Yeah, I think it's a really good comment, and I guess it's something that I've clearly grappled with a bit, because I think, yeah, like porosity, for example, in electrodes is something that is the same in the catalyst layer of a fuel cell or an electrolyzer as it is in a battery cathode. But I guess the size of those pores is slightly different, and the way that we manufacture them is different. And yeah, even manufacturing techniques, like if you're manufacturing a lithium-ion battery cathode, you'll probably make a slurry with NMP, and then you'll doctor blade that onto your substrate. In a fuel cell, we would hardly ever doctor blade. We would ultrasonic spray. I guess, the reason for that is because those manufacturing processes result in the kind of porosity or pore size distribution that we want. In terms of what we can learn from each other, I think what would be cool is having a conference or a session on porosity in electrochemical devices rather than batteries and fuel cells separately. So maybe there's lots that we can do in terms of bringing people together who are working on similar problems and different technologies and learn something from each other that way.
Thank you.
Yeah, Jen, very nice talk. Thank you. You're of course aware of that, like X-ray synchrotrons, like the newer generations are even more harmful to the material. And like you can literally see you turn on a beam and like your voltage just drops.
Yeah.
Like what's your take on like addressing that, especially in like terms of degradation in the data?
Good questions, good challenging questions. Yeah. One thing I suppose you could consider is how much data do you need to collect? So you might be able to get away with taking fewer samples. So you're turning the beam on for a short amount of time, but you're turning it on less. That's a very vague answer. I don't know. Paul, do you have any?
Yeah, so I mean, I think that reconstruction algorithms can work with relatively sparse data sets. So I think particularly you mentioned about AI, right? So you get sort of in-painting techniques, which are pretty commonly used in low-dose electron microscopy. They're not used as often in X-ray tomography and in neutron tomography. So I think that, yeah, sort of the AI-informed reconstruction algorithms are really much better at dealing with noisy data compared with regular filtered back projection. I also think there's a bit of a mindset problem. Gargi and I were talking about this earlier on today. This is not Gargi's mindset problem, it's a general community mindset problem. In that when you want to take an X-ray tomograph, we often sort of oversample the data a lot, particularly when you think about the pixel in the very center of your field of view gets massively oversampled during the rotation, hundreds of times oversampled. And actually, we can deal with much shorter exposures through better reconstruction algorithms, which gives you noisy data. We can also deal with a lot fewer projections. I think that you showed in some of your neutron imaging when you've gone to 36 and then down to 18 seconds. I don't know if you remember how many projections that was. Roughly. I mean, often there's a default, people do thousands and they get away with hundreds. You can probably get away with tens.
Yeah. So, but yeah, no, it's definitely on the order of thousands. But I think the other thing is that we were reconstructing every 180 degrees rather than 360. So I guess that's another option as well, is that although we were rotating continuously, we could then reconstruct every 180 rotation. So maybe we only need to do 180 degrees rather than 360.
Yeah, I think you're right, because again, there's another point where people often consider if you're doing continuous rotation scans, you're still reconstructing discrete steps.
Yeah,
you could reconstruct in a much more continuous fashion. So people tend to reconstruct angle 1 to 180 and then angle 180 to 360. You could reconstruct 7 degrees to 187 degrees and then do a much more continuous reconstruction. So I think it's a bit of a mindset shift that's needed.
Question is probably, do you have any tips when you just have to kill the fish? And I mean, from my experience, then you tend to just make assumptions, right? And then afterwards, you can only disclose what it's not rather than what it is.
Yeah.
Do you have any tips in that kind of workflow somehow?
I guess it always comes back to the research question. What are you trying to find out by doing that ex situ method? And so, yeah, I mean, if you had a specific example, we can discuss it after maybe. But yeah, I think asking what the research question is. So if you could do both, then maybe that's the ideal solution. And it's something I've thought about a bit as well, is like you have to make a lot of concessions when you do in situ imaging, because your cell has to be a bit smaller. It's not got the usual kind of compression because you're optimizing it for this imaging rather than optimizing it for performance. So maybe you could do one study where you use some in situ method in your concessionary cell to look at the start and the end and the middle, and then you have your normal cell where you maybe scan a sample at the start, and then you have a different cell that you've run in the normal way to degrade it, and then you also do ex situ imaging on that degraded one, for example, and then you compare the ex situ degraded to your in situ degraded and see whether they match up. And if they do, I think that's the best outcome. Yeah, I don't know if that answers the question at all.
You can do it in situ at all, but it's just some other.
Yeah, let's do that.
Thank you.
Any other questions? Simon first. Okay.
So I've been in a position when I was in my PhD of doing a lot of limited angle X-ray tomography, where the limitation was imposed by the physical environment that I was doing inside the beamline. Mm-hmm. Are you aware of how at the time it was a problem in terms of reconstructions, but are you aware of like these AI algorithms, how much they're helping with those kind of situations where you've got a very limited number of projections?
Yeah, so again, I'm not fully up on it, but I expect that they'll probably go a long way, as Paul said earlier, to kind of infill some of those projections that are happening in the kind of limited angles. But yeah, I don't know how limited these angles are, but as long as you can get 180 rotation, then
went round, and we had the 10 degrees each time we were missing. There were parts that were missing, and they weren't always it wasn't always linear. You know,
Yeah.
and that there would be like there would be a part that would be obscured, about 10 degrees obscured, and then suddenly you're into the next one.
Yeah. I don't know if you have any.
I didn't fully hear the question. Is this by what the minimum viable rotation?
Limited angle.
And where it's not linear, the number of where the limitations in terms of the number of angles are changing in the size each time because of the equipment.
Yeah, so I mean, I think again, if you look to the people who are doing TM tomography, because you're always rotating around the microscope pole piece, I mean, they rarely get more than 150 degrees, and you still manage through iterative reconstruction algorithms to reconstruction. So yeah, I think 150 is probably okay. You've probably done some, Isabel. I don't know what you've got away with, 160, 170 in X-rays. So yes, it's definitely possible. In terms of then not having uniform increments between the different rotational steps, that's definitely okay. People do a technique called golden ratio scanning, which then takes a fairly kind of, it's not stochastic, but a non-linear approach to the angular selection. So most of the reconstruction algorithms will work that.
I guess the other thing is, again, coming back to this thing of could you do an ex situ study on the material without all of the extra equipment around it, and then you could do your limited angle tomography and do some AI infilling.
That I think would have been quite useful.
Yeah, and then if those two things match, then you know that you can get away with the kind of limited projections.
Even more than that, and actually with your raising standards and characterization theme in mind, you could take any data set, just select 170 degrees worth of rotation, take a full 360 degree rotation, and then stepwise select 170 degrees and 165, and then see what you do begin to introduce artifacts, but you would be able to know what.
Hopefully a bit easier this time. You're talking about taking examples from like IL to ether, for example. Like I know for batteries, you've got like lithium-ion batteries got nickel in there, which just like gets radioactive quite easily and quite strongly. How does it affect fuel cells?
So aluminium can be a problem depending on the grade of aluminium you use. So in theory, there is an aluminium grade that is not so bad in terms of radioactivity, but it would always probably go into quarantine afterwards. And particularly in these cells, because we were having to coat with gold to make it more conductive. I think gold was pretty bad in terms of the radioactivity. I suppose the solution to that is that you just have to do your X-ray imaging first, and then you do your neutron imaging second. Cells with it. Yeah.
Any final questions? Perhaps I'll ask one then. So in your final couple of slides, you talked about the different strategies to improve material sustainability, and one of them was the 1,000,000 mile battery, which was, sort of make it last longer.
Yeah.
I think number 3 was to use less stuff.
Yeah.
But actually, those two are slightly in tension, because the way that the Jeff Dahn 1,000,000 mile battery works is actually by fairly substantially over-speccing the battery, then using a really narrow potential window.
Yeah.
So how do you sort of navigate that tightrope between the ambition to use less, but also make it last longer?
Yeah, I think the answer to that is what's your target application, and like I think the Tesla example, when I remember it being in the news a few years ago, when some people got a certain software upgrade unlocked because of some wildfires in California or somewhere, and so everyone was driving around the same Tesla, but they just accessed a different software package that meant that person A would have 300-mile range and person B would have 200-mile range. So in that case, from a manufacturing perspective, it's really easy because you've got the same kind of manufacturing line to make those cells. But in practice, it just means that some people are driving around this extra capacity that they're not able to access. So I think really we have to think a lot about what is the application. If we want something to perform really well for a long, long time, say stationary storage, like you want to put an electrolyzer in a turbine rig out in the sea, then maybe you can get away with using more materials. But if you want something that's more lightweight and a bit more kind of dynamic in operation, and you can afford for it not to be as long, maybe you can get away with And if your recycling strategies are good as well, then you can kind of get away with something that maybe doesn't last as long but has lower burdens.
Right. In which case, thank you very much, Jennifer.